everyone. Here's our final report for our project, Infectious Disease Models, Pandemic Spreading Simulation for Supermarket. So our report basically has 4 parts. The first is like our motivation for this project. So like why we want to investigating the infectious disease model. And then we will have like a brief introduction on our model. We designed the agent-based model, and then we'll like cover the analysis and conclusion, which including like 3 metrics with 4 parameters, and also like implementations on the social policy. And at last, we will go through our learning experience during the project. Then we move to the motivation part.
As all of our teammates live in NYC, where it was a center of the COVID-19 early phase, we always wondered what can be done. And our motivation wasn't completely the same initially. Some of our teammates suffered COVID-19, and some of us were eager to do something about it and draw a meaningful conclusion from this project. But we had one thing in common, that is, we want to try things through this research that can be actually helpful. We're being exposed to lots of news articles containing the phrases and titles you can see in these slides. Have you ever wondered how much social distancing and wearing masks affect infection rate? With Professor Dieker's guidance, we set this as one of the goals in this research project. Now let's move on to model introduction.
So this is a basic introduction to the model. So what we used is called an agent-based model. So in this case, we have a grid, which represents the supermarket, and each agent is a person, a customer at the supermarket. So if you look at the grid in the corner, we have them moving about in the supermarket, and the blue ones are healthy agents, the yellow ones are infected. So at each time step, which is at each interval of time, all of them can choose to move to an adjacent cell, another position in the supermarket, and then they can come into contact with other agents, and there's a transmission probability, so they have a chance to get infected. And they can move in pretty much any direction, but we have sort of specified the directions and moving patterns, which are coming up next. So an agent-based model. So why did we pick this? So the other alternative is like using equations, but if you use those, you can actually represent the space of the supermarket. Another advantage with ABMs is that you can have identifiable agents. So each one has certain characteristics which can be customized. You can choose a certain thing like randomly. For example, you can make some of the agents socially distanced, which means they'll be cautious. So the way that's implemented is that they try and move to adjacent squares with the fewest neighbors. So they make a list of the safest squares around them, and they choose one of them randomly. So some people do that. Some are infected to begin with in the supermarket, and some of them choose to wear masks. So that's pretty much it. And we used a library called Mesa in Python, which has a bunch of grids and schedulers, which helps us work with time steps. And the grids, the one we used here, allows multiple agents in one cell. So next we have more details about the model and the moving patterns we used.
Now we're going to use Mesa to build our own model. The first step to build our model is to know what we want. As we said before, we want to simulate a supermarket with customers shopping and interacting. We split this sentence and we got 3 demands: the supermarket, the customers, and the in-store actions. For the supermarket, we made some layout settings. Like here, we set a square with 30 units side lengths, 2 entries on the left, 2 exits on the right, and we also set some shelves in the supermarket. For the customers, we set 4 parameters based on what we want to do research on: the arrival rate, representing the frequency of customers' arrival; the mask probability, relating to the probability of getting infected; the initial infection probability, deciding how many people are infected at the beginning; the social distancing probability, deciding how strictly people observe the social distancing policy. And the last one is in-store actions. Here we mainly focus on the walking paths because it decides how often they meet each other. The 4 paths represent 4 different shopping habits. In our model, we just combine all of them, and each agent will randomly choose one. We'll make it more close to reality. And following will be our final model.
So here is a visualization of our final model. We choose 3 metrics to evaluate the 4 parameters. The first metric is the final infection proportion, which is calculated by the number of infected people over the number of total people. Second metric is time taken until 70% infection proportion. And the last metric is newly infected ratio, which is calculated by the number of newly infected people over the number of initially infected people. That is how many people get infected by a single originally infected person. For the visualization part, we choose to use box plot. So here's a sample box plot. We do 100 simulations for each of the initial settings. Each of the column represents results from 100 simulations. The value on the x-axis is the parameter values, and the value on the y-axis is the metric values. So here is a result overview. As you can see, each of the parameter affect the metrics. And for example, from the first row, you can see that the max probability have large effects on all of the three metrics. And on the third row, the initial infection proportion actually has almost no effect on all of the three metrics. And we choose 4 graphs to do further analysis. The first graph is how max probability affect the final infection ratio. As you can see here, there's a ladder shape decrease in the final infection proportion as the max probability increases. And from the second graph is how arrival rate affects the time taken before 70% infection proportion. The graph follows a negative logarithm shape. It decreases very fast at first, but the decrease starts to slow down when it reaches a certain percentage. The third graph is how initial infection probability affect the final infection probability. It also follows a logarithm shape. It increases very fast at first, but after it reaches a certain percentage, the increase starts to slow down. The last graph is how social distancing probability affect the time taken before 70% infection proportion. There's a smooth increasing in the time taken to reach 70% infection as more people being cautious.
Based on our previous parameter analysis, we concluded some insights, especially for social policies. First, we could adjust the intensity of social policy according to the initial infection probability and never let it exceed the threshold. Second, as we discussed before, wearing mask is always an effective measure to control the pandemic. The more strictly it is, the better the effect is. Next, the cautious probability, which is also refers to an indicator for social distancing. It is quite helpful to slow down the spread of the disease. And the last one is about the entering rate, which is also refers to the lambda. When we control and limit the entering rate, the intensity and the spread of the virus spread could be decreased a lot. In a word, we believe that it would be significant if we could consider those factors when we make the social policies. The next comes to our learning experience from this project.
So what's our learning experience from the project? So we basically go through 3 stages. The first stage is exploration stage, that we explore all the related topic to the infectious disease model. We brainstorming and research separately. And then with the guide of our professor, we move to the second stage, collaboration. So we have a research focus, and we research and work as a team to construct our model for the disease spreading simulation. Then we move to the final innovation stage, that we add our creativity to the model. Like we design our own model with features, parameters we want to put into, that we really learn to work as a team through this project. So that is all for our final report for the project infectious disease model. Thank you for your watching.
Thank you.